Dear students, in our last lecture we discussed the basic principles and the construction of an induction machine. In this lecture we'll be discussing the EMF induced in an induction machine. We know that the application of three-phase currents to the stator windings of an induction machine results in production of a rotating magnetic field in the air gap. As the magnetic field rotates in the air gap, the magnetic field cuts the stator windings as well as the rotor windings, and therefore an EMF is induced in the stator as well as the rotor windings. The aim here is to derive expression for the EMF induced in the stator and the rotor windings, and we'll begin with the EMF induced in the stator windings. For this, we'll initially consider a two-pole machine for the sake of simplicity, and we'll assume that there is a rotating magnetic field in the air gap which rotates at a speed omega s radians per second in the counterclockwise direction. And we'll assume that at time t equal to 0, the field axis of the rotating magnetic field is aligned along the stator phase A axis. This is the stator phase A axis, and the magnetic field axis is initially assumed to be along this line. It means that there will be a north pole in the left half of the stator and a south pole in the right half of the stator, and the center of the north pole will be here and the center of the south pole will be here. Now, since the magnetic field is sinusoidally distributed in the air gap, the magnetic flux density can be plotted as function of the space variable theta as shown in this figure. The magnetic flux density varies sinusoidally, and here along the stator phase A axis, the magnetic flux density is maximum initially. The rotation of the magnetic field in the air gap in this figure will correspond to the movement of this sinusoidal wave towards right at a speed omega s. And we have also shown the position of the coil sides of phase A winding in this figure. We have coil side A at minus pi by 2, coil side A prime at pi by 2, and then these will repeat and we can draw it as many times as possible. Therefore, as the magnetic flux density wave moves towards right, what happens? The flux density initially at the location of coil side A prime will be 0, and then as the wave starts moving towards right, the magnetic flux density will gradually start increasing as a sine function, and therefore the magnetic flux density at A prime location will be given by Bt equal to B peak sine omega st, where B peak is the maximum value of the flux density wave, which corresponds to this point B peak. Then let us assume that the length of the stator core is L and the radius of the air gap be R. Then the EMF induced in one conductor of the coil side A prime, we'll consider one conductor of this coil side A prime, it will be given by EZT equal to the well-known equation BLV, and B is B peak sine omega st at this point into L into V will be equal to R into omega s. V is the relative velocity between the conductors and the field, and is given by this expression. So we can rearrange this as B peak LR omega S sine omega ST, and if we have a look at this expression, it is half the flux per pole, 5 by 2, therefore it will be 5 by 2 omega S sine omega ST. The direction of the EMF induced in a conductor of coil side A prime can be found by using V cross B rule, and where V is the velocity of the conductor relative to the field. Here the field is moving towards left, and therefore the velocity of the conductor relative to the field will be towards right. And B is directed upwards because initially the flux was directed towards right, and as it rotates, the flux here will be passing from the rotor to the stator, and therefore B will be directed upwards. And then using V cross B rule, if we rotate a screw from the direction of V to the direction of B, it will come out. Therefore the direction of the induced EMF will be outwards at this location. The EMF induced in a conductor of coil side A will have the same magnitude, but will be directed inwards. Using V cross B rule again, the field is moving towards right. It means that the conductor relative to the field has a velocity towards left. B is again directed upwards, and using V cross B rule, the direction of the induced EMF will be inwards in a conductor of coil side A. And we know that the conductors of coil side A and A prime are connected in series to form turns, and they are connected so that their EMFs are additive in nature, as has been shown in this for one turn. So we see that the EMFs are additive, and therefore EMF per turn will be equal to twice EMF induced per conductor, which will be of course equal to phi omega S sine omega ST. If the phase A winding has n1 number of series turns which are assumed concentrated, then the EMF induced per phase will be equal to the number of turns into the EMF induced per turn. So it will be n1 phi omega S sine omega ST. So this is the expression for the EMF induced in phase A winding. Now, since the windings of different phases are of identical design, the EMF induced in phases B and C will be of equal magnitude, but there will be a relative phase displacement of 120 degrees between the EMFs. So in general, the EMF induced per phase is given by this expression. So this all this we have discussed for a two-pole machine, and let's see what is the change that has to be made for a p-pole machine. For a p-pole machine, as far as the flux density in the air gap is concerned, it will vary again in the same fashion as for a two-pole machine, but when the angle is measured as an electrical angle, and therefore we'll have the expression for EMF induced in one conductor, which will be equal to BLV. We'll again have B peak sine omega ST, but omega S measured in electrical radians per second. Then we have L into R omega S again, but omega S here, since it's the actual speed between the field and the conductor, therefore here we'll use omega S measured in mechanical radians per second. Omega SE is in electrical radians, and omega SM is in mechanical radians per second. And we know the relationship between the mechanical angle and the electrical angle. Omega SM will be equal to 2 upon P omega S E. And using these two expressions, we'll have therefore EZT, EMF induced per conductor, will be equal to 2 upon P V peak LR omega SE sine omega SE. We have made here a substitution for omega SM as 2 upon P omega SE. And we can again see that as far as this expression is concerned, this is equal to half of the flux per pole, because for a p pole machine the flux per pole is 4 upon p b peak LR, and therefore this quantity is 5 by 2 into omega SE sine omega SE into T, where phi is the flux per pole. The EMF per turn will be twice Ez, therefore it will be phi omega SE sine omega ST. And since we have assumed n1 number of series turns per phase which are concentrated, the EMF induced in the phase A winding will be given by this expression. So it is n1 times ETT. And if we compare this equation with the equation obtained for two-pole machine, we can see that the two equations are in fact same, except that omega S has to be measured as an electrical in electrical radians per second. So therefore equation 8 is the general expression for the EMF induced, and hence fourth we'll be dropping the subscript E, and we'll keep in mind that omega has always to be in electrical radians per second, and the general expression for the EMF induced per phase of the stator will therefore be n1 phi omega S sine omega S T. And we know that now the speed omega S is the speed of the rotating magnetic field in electrical radians per second, and we have already seen that this speed is also equal to omega, which is the angular frequency of the stator currents, and omega we know is 2 pi f, and hence we can write E1 can also be written as n1 phi into 2 pi f into sine 2 pi f into t. And therefore we can easily see that as far as this expression is concerned, in this expression the frequency, this determines the frequency of the induced EMF. We'll see that the frequency of the induced EMF is equal to the frequency of the stator currents. Therefore we can write F1, one subscript will be used for the stator quantities. So as we have done here also, E1 is the EMF induced per phase of stator. Similarly, F1 is the frequency of the stator induced EMF, which will be equal to F, where F is the frequency of the stator currents. Now, the RMS value of this induced EMF will be given by, this is the peak value divided by root 2. So it will be equal to n1 phi into 2 pi f divided by root 2, which can be written as root 2 pi f phi n1. And we know that this comes out to be equal to 4.44 into f phi n1. Therefore the EMF induced per phase is equal to 4.44 f phi n1. And if you have a look at this expression, it is quite similar to that obtained for a transformer. In case of transformer, f is the frequency, and phi, instead of phi we have there, we write it usually as phi m, where phi m is the maximum value of the flux passing through the core of the transformer, because we see in that case the EMF is induced because of changing flux, and the flux increases from 0 to its varying sinusoidally, and therefore we take the maximum value of the flux in case of a transformer. But here we take the flux per pole. In fact, this is the maximum flux that can link a coil, because the maximum flux that can pass through a coil is equal to the flux per pole. It's in fact effectively the same expression. In case of transformer, we have the EMF induced due to the changing flux. Here we have the EMF induced due to the motion between the field and the conductors. In deriving the expression for the EMF induced in the stator windings, we have considered a concentrated coil. Let's see what's the effect of distributed winding. We know that distributed winding is kept in different slot pairs. We have more than one slot pair per pole pair, and here for the sake of simplicity I have shown 3 slot pairs per pole pair, and the angle between the slots, successive slots, is the slot angle denoted by gamma. And here we'll express gamma in terms of electrical as an electrical angle. Therefore, what will happen is when the phase A winding is distributed in different slot pairs, if we consider a coil which is in this slot pair, there will be an EMF induced in this coil, and as far as the EMF induced in this coil is concerned, it will be equal in magnitude, but it will be displaced in phase from the EMF induced in this coil. Similarly, for the third coil, and because of the phase difference between the EMFs induced in different parts of the same phase winding, what will happen? The net EMF will be less than the algebraic sum of the individual EMFs, because in AC it's not the algebraic sum which is taken, we take the phasor sum of the EMFs. And now, since there is a phase displacement between the three phasors, there is a phase displacement between the three phasors of gamma, the net EMF will be less than the algebraic sum of the three EMFs. So what we see is the net EMF is less than the algebraic sum of the individual EMFs of the winding segments, and the factor by which it will be lesser is known as the distribution factor, and it is usually denoted by KD. Some authors call it as breadth factor and denoted by KB. Now, therefore, when we use distributed winding, the EMF induced will not be given by just this expression, it has to be multiplied by a factor KD, and for the stator we'll use KD1. So KD1 is the distribution factor of stator windings, and we should know that KD is always less than 1 for a distributed winding. Now, in AC machines, not only do we use distributed windings, we usually go for short pitched windings also. Instead of using full pitched coils, we use short pitched coils for certain advantages, as will be discussed later. Now, what will happen in that case? Again, if we consider a full pitched coil, we have seen that the EMF induced in the two conductors of each turn will be same in magnitude, and they will be in fact phase if we consider as far as the connection between the two sides or the two conductors of a turn is concerned, they are additive. But if we use a short pitched coil, what will happen? If we have a conductor, one conductor of a turn here, another conductor will be somewhere here. Therefore, again, the EMFs induced in the two sides of each coil will be out of phase, and therefore the net EMF again in each turn will be lesser than twice. We cannot multiply it simply by 2, so it will be lesser than twice EMF induced in each conductor, and hence the effect of short pitched winding is again to decrease the induced EMF in the machine by a factor known as pitch factor, and therefore the EMF equation has to be further multiplied by Kp1, where Kp1 is the pitch factor of stator windings. We can write therefore the EMF equation as 4.44 F phi N1 Kd1 Kp1, which can further be written as 4.44 F phi N1 Kw1, where we combine these two factors together. The product of the distribution factor and the pitch factor is known as stator winding factor. So this is therefore the final expression for the EMF induced in the stator windings when we use short pitched winding and distributed winding. So let's now discuss the EMF induced in the rotor windings. And we again know that we have a rotating magnetic field which is rotating in the counterclockwise direction at a speed omega s radians per second. Now we have a rotor, and suppose the rotor is rotating in the direction of the rotating magnetic field at a speed omega r, both expressed in radians per second but as an electrical angle. Therefore, the rotating magnetic field will be rotating with respect to the rotor at a speed which is omega s minus omega r. And as far as the equation for the EMF induced in the rotor windings is concerned, the equation will be similar to that of the stator, except for the fact that the number of turns per phase of the rotor can be different, and also the speed in the expression will also be different. We'll have, if we have n2 number of turns per phase of rotor, and we have the speed between the rotor and the rotating magnetic field, the speed is omega s minus omega r, and therefore we can write the equation for the EMF induced per phase of rotor as n2 phi. We had in the other one n1 phi, and then we had omega s there. Instead of omega s, we have omega s minus omega r, the relative speed between the field and the rotor, into sine, similarly, omega s minus omega r t. Now, we can simplify this expression by defining a couple of terms. One is known as slip speed. It's the difference speed, omega s minus omega r. And then we define slip s as omega s minus omega r by omega s. That means it is the slip speed expressed as a fraction of the synchronous speed. Now, since this is a ratio, it is immaterial in what will be the units of these, whether these are electrical radians or mechanical radians, that will not matter. This is a dimensionless quantity s, and instead of using, in fact, the speeds as radians per second, we can use in RPS also. Therefore, it can be ns minus nr ns minus nr by ns, where these are the speeds in RPS. Or it can also be written as ns minus nr by ns, where ns is the synchronous speed in RPM, nr is the rotor speed in RPM divided by ns. Now, from the previous expression which we had used for defining the slip, we can write omega s minus omega r as s times omega s, and therefore equation 17 can also be written as this equation. We can substitute for omega s minus omega r at both these places, and therefore it can be written as e to t will be equal to n2 phi s omega s into sine s omega st. Now, omega s is equal to 2 pi f. Therefore, if we put here 2 pi f, we can see that the multiple of 2 pi t is actually the frequency. Therefore, the frequency of the rotor induced EMF will be given by, we denote it by f2, it will be equal to s into f, and f is same as f1, Therefore, we can write F2 is equal to S times F1. Now, the RMS value of the EMF induced per phase of the rotor will be given by, it will be peak value divided by root 2, which can be written as N2 phi S into 2 pi F divided by root 2, which simplifies to root 2 pi SF phi N2, which can further be written as 4.44. This can be written as F2 into phi N2. This is the expression for the EMF induced per phase of the rotor. And with distributed winding and short pitched winding, we'll introduce the corresponding factors, distribution factor and the pitch factor, and therefore the EMF induced per phase of the rotor will finally be given by 4.44 F2 phi N2 kW2, where kW2 is the rotor winding factor, which will in fact be equal to Kp2, where Kp2 is the pitch factor of rotor winding, into Kd2, where Kd2 is the distribution factor of the rotor windings. Now we have seen that the frequency of the rotor induced EMF is equal to S into frequency of the stator EMF, and therefore we see that if the rotor rotates at the speed of the rotating magnetic field, that is omega R is equal to omega S, we can easily see that at that time S, the self, will be equal to 0. We can see that the EMF induced in the rotor windings, because this is S into F1, it will be equal to EMF will be equal to 0, and the frequency obviously has got no meaning. Now, if the rotor stands still, that is omega R is equal to 0, this was the first case. This is the second case, that omega R is equal to 0. In that case, it can be seen that S will be equal to 1, and therefore we can see that F2, the frequency of the rotor induced EMF, will be equal to the frequency of the stator induced EMF. And one more thing can be seen, that if omega R is less than omega S, that is, the rotor is rotating at a speed less than synchronous speed in the direction of the rotating magnetic field, in that case it can easily be seen that the slip will be less than 1, and therefore the frequency of the rotor induced EMF will be less than the frequency of the stator EMF. There is one more case. If we assume that the rotor is rotating in a direction opposite to the rotating magnetic field, so it is rotating, omega R will be, in fact, in that case we can treat it as negative, and we can easily see that the silp will have a value greater than 1, and in that case the frequency of the rotor induced EMF will be greater than F1. So these are different cases. We can see that when the rotor rotates at synchronous speed, no EMF is induced in the rotor windings because the silp is 0. When the rotor stands still, the silp will be equal to 1, and the frequency of rotor induced EMF is same as the frequency of the stator EMF. Third case is when the rotor is rotating in the direction of rotating magnetic field at a speed less than the synchronous speed, then the silp will be less than 1, and frequency of the rotor induced EMF will be less than frequency of the stator EMF. And then the next case is when the rotor is rotating in a direction opposite to the rotating magnetic field. In that case, omega R will be negative, and if we have a look at the expression, this we'll have omega S minus omega R, it will be a negative quantity. Therefore, we'll see that self will be greater than 1, and therefore the EMF induced in the rotor will have a frequency greater than the frequency of the stator induced EMF. So we'll close here. In the next lecture we'll solve some numerical problems on this. Thank you.